So I'm going to share my slides, which were prepared by FASE organizers. So welcome to Fabrication Sculpting event of SMI 2020 conference. So it's a specialized segment of the conference in which art meets, maybe I can make it full screen. Actually, it's quite tricky to make it full screen without. Sorry for that. Technical aspects. Here goes. So yes, it's actually the segment of the conference in which arts meets the science, sculpting meets fabrication in terms of artistic and not only artistic and technical aspects. So on this fabrication events this year, we received 9 submissions. 4 of these 9 submissions were accepted as full papers and will be presented shortly after my short talk. And further 4 will be presented as extended abstracts, like a posters which discuss a wide range of topics and views on fabrication process and linked to artistically interesting artifacts. So the posters will be presented tomorrow, approximately the same time, and the full papers will be presented now. But before we're doing that, I'd like to pay tribute to Nat Friedman, who was one of the pioneers of art and mathematics movements. And in some way, he was one of the founding members of this very segment, because many years ago, Nat Friedman founded Art and Mathematics Conference, which was president of FASE. So Nat Friedman received his PhD in mathematics from Brown University in 1964, and he was a professor of mathematics in State University of New York at Albany from 68 to 20,000. So Nat made enormous impact in early years of ergodic theory and measurable dynamics, but also he began being practiced in sculpture in the 70s. And eventually he was known not only in mathematics, but in sculpting as well. Unfortunately, he passed away of COVID-19 complications early this year, but he will be remembered, and that's why we dedicate these fabrication sculpting events to Nat. Right, and now we've got 4 full papers for fabrication sculpting this year, all very different, but all very exciting. And I'd like to welcome the first presenter. We're going to make a co-host now. Misha Vu from Bournemouth University with a talk called A Feast for the Eyes, visualizing favorite to vision synesthesia. So Misha, up to you, please.
Thank you. Can you hear me?
Yes, we can hear you.
Okay, I'll share my screen now. Okay. Hello, my name is Meija Wu, and I'm going to present the paper written with my co-author Oliver Gingrich on flavor to vision. Sorry, flavor to vision synesthesia. In this presentation, I will detail how we gain insight into a rare neurological condition called synesthesia and developed an original method to design and produce 3D artifacts to creatively visualize the abstract concept of synesthesia. I would like to apologize in advance because I'm going to be saying the word synesthesia many times in this presentation, so please bear with me. Some of you might be quite unfamiliar with the term synesthesia. Scientifically, synesthesia refers to the perceptual phenomenon in which the stimulation of one sensory or cognitive pathway triggers the response of another sense on top of the original one. In our project, we focus on a rarer subtype of synesthesia called flavor-to-vision synesthesia. This is when a person can see abstract visual elements whilst tasting the flavors of food. For example, when we eat cake, we perceive it as being sweet, but to a synesthete or someone with synesthesia, he might be simultaneously seeing abstract shapes and colors. That is his brain's response to the sweet flavor. There are two types of synesthetic experiences. One is projective, which is when a person is able to vividly project a vision on top of his normal vision, or the mind's eye. The other is associative, which is more of a strong feeling or instinct. Synesthetic experiences are involuntary, immediate, and consistent. This means that the visions or feelings produced do not involve any deliberate imagination. The most important trait to note is that synesthetic experiences are idiosyncratic. This means that it is different from person to person, and this will be apparent as we dive deeper into this presentation. Because synesthesia is still largely unknown and misunderstood by many people, due to the fact that only a small percentage of the population experiences it, and the fact that it doesn't generate any external evidence that the general public can see, it is harder for a synesthete to prove that he or she can experience such abstract visions, for example. Because synesthesia and flavor are both very abstract concepts to visualize, we looked at several existing works done by other people, from which an experimental live action animation and an advertising campaign for Heinz beans were the two of our biggest inspirations. Learning from these projects, we decided to make use of 3D printing to produce tangible artifacts that provides a more intimate and believable viewing experience. We also wanted to integrate 3D printed parts with real props, so the result is surreal but impactful. Because my co-author and I do not have synesthesia, we carried out qualitative participant studies with real synesthetes to understand their flavor experience. We recruited 3 participants from around the world who qualified for our study, and we conducted interviews and asked them to keep a visual diary of their synesthetic vision depictions over the course of 1 week. From the visual depictions provided by the participants, we found that each of our participants was able to perceptually experience flavors in very different ways. The first participant saw 2-dimensional shapes that can be interpreted as flavor profile of the food that he tastes. In the case of this particular participant, we found that simple flavors produce more distinct shapes, while more complex flavors actually had less defined shapes. With the participant's love for coffee, we were able to see that he consistently depicted a similar hat-like shape for the different types of coffee. And we interpreted that the round top part of the shape belonged to the sweet and creamy flavors of milk and sugar, while the flatter bottom part belonged to the bitterness of coffee itself. The second participant sees flavors in the form of colors and textures in 3-dimensional space. From the color data obtained from the participant, we found that food belonging to the same food groups often produce similar colors. For example, meat and dairy tend to be in a shade of blue, vegetables were mostly pink and purple, and seafood were orange. Because of this characteristic, it makes the identification of every component within a complex meal much easier. For example, in his description of chili mac, the tomato sauce of the dish caused him to see a gray background covering almost all of his vision in the texture of ash, on top of which he sees the flavor of minced beef appearing as specks of blue with oily reflectivity. And dusted over everything was the macaroni flavor in the form of purple powder. I'm sure this is very abstract for many people to understand, but later we'll explain how we managed to turn that into a 3D design. The third participant, synesthesia, produces even more abstract images, as you can see here. These images compose of shapes, lines, and colors, and sometimes they don't have a solid border. The participant explained to us that this was when the images extended beyond the limits of her vision. Because we were only able to collect a small sample of sketches from the participant, it was not enough for us to compare and interpret the drawings. Apart from the depictions of cranberry sauce and cranberry cookies, which both had red and sharp shapes that we believe to originate from the sweet and tart flavors of cranberry. After having studied the three participants, we can see that trends can be found within each participant's unique cases of synesthesia. However, there was barely any similarity between the three participants. Because of this, we decided to develop 3 personalized artifact designs based on each participant to demonstrate the idiosyncrasy and the wide spectrum of flavor to vision synesthesia. Instead of creating just one artifact that attempts to generalize all possible experiences. This also meant that in the future, if we find more participants, we can always expand our collection. The design approach we took was to transform one of each participant's depiction into the literal form of their real-world food counterparts. Apart from the one in the middle, which, because it was quite abstract, we had to interpret it into a equally abstract design to show the layering and the different textures that the participant actually saw. Here is a flow chart that shows how our final artifacts were produced from each of our participant studies. The blue bubbles are the pre-production stage, where we carried out printing tests to familiarize ourselves with the 3D printing procedures to avoid making mistakes down the line and to reduce possible waste of time and material cost. We also tested with 2 different printing filaments available at the university, CPE and PLA, and found that they made little difference after being painted, but CPE generally produced a rougher result and were more prone to printing accidents. We also tried to test coating the painted models with various surface varnishes, which added more reflective qualities that could be very useful in recreating the texture of food, because otherwise all of the models would be non-reflective. We started by studying surface textures of real food and applying them using 3D sculpting techniques inside ZBrush, as well as the printer settings. For example, to create a pile of ash, there was an experimental setting in the printer software Automaker Cura, which could tell the printer to print the surface of a cone model in a jittery motion, therefore creating a fuzzy effect, which was much more efficient than manually sculpting and printing the textural detail of ash. We then employed traditional painting techniques to further mimic the translucency of food because the printed material themselves were not see-through. We also used surface varnishes to treat the painted sculptures. We found that glossy spray paints gave the printed models highlights that are similar to grease, while resin produced more reflective coating that looks similar to liquids or honey. By creating a combination of these different levels of reflectivity, we try to make the sculptures look more believable. Here are the final 3 sculptures that we produced based on 3 real cases of flavor to vision synesthesia. The end result was very close to our intended designs, which demonstrated 3D printing's ability to accurately materialize conceptual designs with a substantial degree of creative freedom. The use of 3D printing meant that the same artifact design could be reproduced for artistic experimentations. In the case of this project, we were able to try out different printing and painting tests until we arrived at a desired outcome. This demonstrated the application of 3D printing in the designing and making of artistic sculptures. However, our research also had some weaknesses. Because the framework we established is under the assumptions that the artist has an adequate knowledge of 3D modeling, sculpting, and 3D printing. And we followed an artistic approach to visualizing synesthetic experiences instead of going for an accurate representation. This meant that the viewers might be misled to think that these sculptures are actually what the synesthetes saw. In which case, we recommend that a more accurate representation of synesthesia can be made using, for example, VR technology, where the viewers can see augmented visions from a first-person perspective, similar to how a synesthete would. To improve the project, different 3D printing materials can be explored, as there is definitely more room for improvements to push the results to be more photorealistic and believable. We also think that if we could recruit more participants and collect more visual data to start analyzing the trends and links on a more scientific level and a deeper understanding of flavor-related synesthesia can potentially inspire new food packaging and design. In conclusion, we consider our project to be successful. The goal of this multidisciplinary project was to conceptualize flavor to vision synesthesia and to find a way to creatively visualize it in a way that would be accessible for the general public, in which we chose to make artistic sculptures that could be exhibited in public to raise more awareness and serve as something the synesthetic community can identify with. We created 3 designs based on our participant studies and identified a functioning framework of producing artifacts using 3D printing. That was the end of the presentation. Thank you for your attention, and feel free to ask any questions.
Thank you, Meija. Great results. So, yes, any questions? Please write into the chat. So, a question from Tim. Did you show any of the prints to one of the people with synesthesia?
Yes, I actually showed it to 2 of our participants. One of them, I wasn't able to get in touch with them, but what they said was they do not represent what they actually saw, because what they saw was 2D shapes and that are actually in their vision. And what we made was combining what they saw with actual food, which is more of a artistic and interpretive approach. So they said it was not accurate, but they actually liked it, and they felt like they could show it to their friends and family and to prove that it was what they experience is real.
Okay. So I've got a question for you, by the way. So it sounds like it was quite hard to find participants with this condition. Do you know how rare this condition is? I mean, how many people in the world have this condition?
Okay, so this is a very interesting one, because a lot of people actually, a lot of synesthetes actually live most of their lives without realizing that what they experience is different from other people. They assume that everyone also saw shapes and colors when they tasted food. So a lot of times there are actually research done to see how prevalent is synesthesia in the general population, but it was difficult. And I think the result ranges from 1 in, I think was the 1% to 0.4%, which sometimes it seems like it's actually much more common than we think. But I think there aren't it's difficult to say because sometimes some of the studies show that it's actually much more common than we think, but there are also other studies saying it's very rare. And in our case, we actually went on to a synesthesia, what do you call it, an online email forum composed of 1,000 synesthetes, at least 1,000 synesthetes. And we sent out emails to them, and only, I think, 9 of them got back. And I guess that shows how many flavor to vision synesthetes are there in the general synesthesia community, because well, I have the stats here. Yeah, there are many different types of synesthesia, at least 73 types. And out of the 1,000 people we contacted, only 9 of them got back. And at the end, only 3 of them actually we were able to get in touch and carry out the study with.
Right. Okay, thank you. Well, I'm going to second the comment that wonderful project, eye-opening. So thank you, Meja.
Thank you.
Clap for you. And we're going to our next presenter, who's going to be Niraj Yadav, with a talk called Interlocking Worlds by Voronoi Decomposition of 3D Space.
Hi, thank you so much for the introduction. And yeah, let me just begin by saying thank you for giving me this platform to present the work, and I hope you guys enjoy it. So very recently, additive manufacturing has entered construction, and it's being touted as the age that will transform the industry. But as you can see from the image, the issue is if we start 3D printing buildings and structures, our 3D printers have to be bigger than the building itself, which does not seem very efficient. So another approach is to use modules to construct buildings. And this is not something new. I mean, we have been constructing modular structures for a while now, from Stonehenge to Abel's Vault and more. So, and in fact, I myself tried a few of them. I used to think of some ideas, print them out and see how they're interlocking and if it's well or not. But this also wasn't a very efficient approach because it was more of a trial and error method. And what I wanted to do was come up with a method to explore this interlocking for single nave barrel walls, and then see if it can be expanded to other structures. Now, once I started exploring interlocking and I wanted to look for a strong method, I came across some recent literature. The Delaunay law was at last year's SMI. Generalized Abel walls was presented earlier today, and they were using Voronoi for interlocking. And this seemed very exciting to me. The concept itself was introduced, way back, and the formulation by actually a French mathematician and one of the original philosophers, René Descartes, and then it was later formulated mathematically by Peter Dirichlet in 2D and 3D, and then expanded to ND by Voronoi. And hence we now commonly refer to as Voronoi itself. So the concept is pretty simple. There are two key parameters, are seed points and then bounding box. So in this case, there are 5 seed points, and you can see how it's being bounded inside a cube structure. So when I was trying to come up with these interlocking systems, one of the key challenge is how do I define the bounding domain for cylindrical or vault structures? So my approach has been to convert the seed points as to a seed point collection, and the bounding domain, instead of fixed boundary, it's also a bounding points that are a collection, and they form the geometry that's going to bound it. If we look at the modules that I'm trying to create, so take a vault and assume it's made of 3 arcs in this case, but it can extend to infinity or indefinitely. So assuming we are trying to come up with the shapes for these modules, if you look on your right, you'll see the angle that is formed by each individual module would be pi by q, where q is the number of modules. And in this study, for the rest of my results, I have used odd number of modules, because in that case, it is ensured that there'll be a module at the center of the structure. So that's why I went for only odd number of modules. And then the gray is the region which I'm trying to have a structure in. So it's basically divided into 3 curves, the 3 black curves that you can see in the figure. The outermost and the innermost curve, they basically guide the form of the structure, the external and internal form, whereas the center curve is the one which determines the interlocking. That's how I've denoted it for the rest of it. And then the interlocking is defined by this angle phi on the center curve. So just a quick walk through. If we take a sectional view, initially there are 2 curves. These are the guide curves. And then I'm translating it in Z direction, both forward and back. And our interlock curve is slightly offset compared to the guide curves. And this is what provides the interlocking in our X and Y coordinates. When I do the translation, I'm doing a slightly different translation. So I'm translating only in one direction, and this provides the interlock in the Z direction. So this is a complete curve set of our modules. And once I have the curves, I can easily decompose them into a certain number of points, 6 in this case. But if it might be obvious that this curve would overlap with the endpoints of this would overlap with the starting points of say the next adjacent curves. So that would create some complications in the computation. And therefore, what I'm doing is I'm removing the endpoints from all the curves. So there's a set of these points corresponding to each module. So this forms the seed points for our computation. For the boundary calculation, if we look back at a structure, assuming that I'm trying to compute the second module represented by number 2, 1 and 3, which are right above and below it, would form the modules that bound it. So the module bound. The highlighted in yellow arches, NX and NZ would form a sort of arch bound to it. And if you look to the right figure, the innermost and the outermost lines in blue and cyan, that's basically what will constrain the geometry from extending indefinitely on the outside as well as the inside. So again, a quick overview of how this looks like. So we have our red points, which are the seed points, and the blue ones are the ones denoting the module bound for the adjacent upper and lower modules. Similarly, we can look at the side arches, which will form a sort of arch bound And then we are trying to constrain the vault itself from growing indefinitely on the outside and inside. And for this, I'm using a different set of points. So if you can see, there's a J number of points for each of these walls. So in this case, J is 100. So we have about 200 points directly in one cross-sectional view and total of 600. And now you might be able to anticipate that if I'm drawing, if I'm computing the Voronoi, it'll likely be at the center of these curves. So this is what the result would be. And as you can notice, the boundary is exactly in between the vault bound and our guide curves. Now, the form we get out of that is something that can be manufactured with the traditional casting methods. However, with additive manufacturing, we are able to further reduce the weight of the modules themselves. And this can be done by just changing it either to a mesh or just reducing, scaling down each faces and extruding them towards the seed points. Later, if this is more creative liberty, if required, Catmull-Clark subdivision can be used. However, it has to be mentioned that the edges have to be kept same or fixed. Otherwise, if the edges changes, the interlocking would be lost, and that's not something favorable. So here's another view of the module along with the seed points that you can see inside the module. Now, as I was mentioning that I've tried to assign only odd number of modules, and that's why that ensures that there'll be a module at the center of it. And since there's a angle phi, which is the interlocking angle offsetting each of the module, the center keystone module is slightly reduced in length because of these. Here are some of the results where each module is slightly different from the other, but since the angles and the angles are same, we can also repeat a same module throughout this structure, except the keystone. Also, the end modules will be slightly different because they don't have a module bound below them. So that would be a different case, but that doesn't restrict us from using the same module over there as well. So I have tried to 3D print some of these, and so this was done using PLA with fusion deposition method. And I've done it on 2 scales. So one on your left is a small scaled version, about 6 inches in height. And you can see the tumbler next to it for reference. And then on your right is now that I'm trying to scale it up, and it's currently in progress. And you can see the scale behind it. So I'm trying to increase the length or the height of it to about 2 feet. There are some challenges there, but I'm making progress on that. And then you can also see that this has been done with very limited support system. And you can see on your right, the only places supports were used and then broken off after the printing towards the interlocking part. Here's a complete assembly made with 6 repetitive modules and 1 keystone module that is separate and unique as compared to others. And it is symmetric, or basically mirror images about the keystone module. So what you notice is the interlock is extruding out of the screen on your left while it's going inside this screen on your left and outside the screen on the right. So this allows the arch, if we have another arch next to it, it will allow interlock in both the directions. Now, if instead of using these 100 points, if I have lesser number of points or more number of points, that introduces these features or these protrusions on the surface. And that again gives slight creative liberty as to how we want to take advantage of these. And in this case, you can actually directly count that there are about 7 points that were used as the inner and outer bonds. Now, if the structure is too off, there's also a possibility to remove these protrusions by certain methods. I have mentioned one in my paper, how I'm using a spring-based system to basically smoothen out those edges, but keeping the interlocking interface or the geometry same. And here's the result of that. But art structures, in general, under their own weight, need some sort of support from outside to constrain it from falling apart, or because of the self-weight and gravity. So this similar method and approach using Voronoi and curves can be used to create end supports and foundations for these sort of vaults. In this case, I've used a hyperbolic vault to depict how a new foundation curves can be introduced, and that can help interlock with the curve and keep it in place, interlock with the vault. Here's a possible assembly sequence. It'll have to be bottom-up approach. So we first start with the foundation, and then these can be interlocked with a simple movement slide. And the only difference in erection movement would be when we are trying to place or connect the foundation to the vault itself. So that'll have a translation in X and Y. But other than that, all the other modules can be connected with the Z direction motions, which is basically coming out of the screen or into the screen. So while I have gotten good results so far, the idea is to further expand it to vault joints, where basically two walls are interlocking at perpendicular. Then how do we want to define the bounding structures is something to look at. Evaluating the performance of interlock itself, the angle, how much difference that interlock angle makes in the stability is something that future studies I plan to look at. Also testing the constructability. Once I have a full-scale module, I plan to test and see how possible it is to construct it without using additional supports and scaffolds. And then also we can explore interwoven curves in the future and play around with it. The modeling was mostly done in Rhinoceros and Grasshopper with a couple of plugins and the printers, and you can see more details in the paper. I can show you a quick, if you have a few more seconds, I can show you how the interface works. I don't know how well this is going to go through over Zoom, but I will upload this video on Discord and share it with the organizers, so you can take a look at it later. So yeah, that's about it. And I just want to thanks Dr. Ergen Eckelman, Dr. Julian Kang, Dr. Wei An for all the discussions we have had so far, and that helped me think through about this project. Also the FASE SMI and SPM chairs and committees, and special thanks to the FASE technical committee and reviewers as well. I would be happy to take any questions now. Thank you.
Thank you, Niraj. So any questions? I don't see anything in chats. maybe the developer is something. I've got a question for you. So basically, your guide curve is an arc.
Yes.
Do you think you can extend that by using more generic quadratic curves like ellipse or parabola or something like that?
Right. Absolutely. So almost all the examples I showed you were with simple semicircular arcs, except the one case where I tried a hyperbola for the construction of things. This one. So yeah, this is a hyperbolic curve, and then I tried some NURBS curves
Right.
to do the foundation design a little, just to ensure that this also works with other curves as well. So that was the idea.
Okay, thanks.
I do have
Carlo,
a question. So once you have put up your points, then the mechanism is very clever to make nice, smoothly touching objects. But it obviously takes some planning of where you're going to put all your domain points. And in particular, you don't just want to make convex tiles, because they would not really support themselves very much. So you have these protrusions where one tile interlocks with the other tile and the like. So what is the high-level process of figuring out in the first place what kind of convoluted shape you want for your modules? And did you do any kind of physical simulation testing up front to see, once you had those modules, whether they really would be very strong and supportive and might even survive an earthquake or something like that?
Yes, thank you so much for that wonderful question. I'll try to answer it as best as I can. So yes, initially I began with very early methods. So you see these interlocking extrusions, which weren't there initially. Or when I started very initially, it was just a minor protrusion, maybe just in one direction in X or just Y. And then I later expanded it to all the three directions. Regarding the structural analysis, I haven't done any computational simulations to see which method performs better or which interlock performs better over the other, but that's something I'm definitely looking at in the future. What I have seen in literature so far is that whenever there's an arch and then there's any sort of earthquake or a lateral load that comes into it, it usually breaks at certain points in the curve. So if you see, if you can see the image, if you see the probably bottom left one, it'll probably break somewhere around those lines when it's under an earthquake load or something, similar lateral load. So having these protrusions actually ensures that the modules in case of these loads will have some flexibility to move around and not be very rigid. Sometimes that's what makes the breaking in simple arches. But again, that's something from literature, and that's what I intuitively feel would help having these interlocks. But I still need to test them on full scale and actual physical models. I hope that.
Thank you very much. Thank you.
Thank you.
Thank you. Any more questions? Well, I guess no further questions. So thank you once again, Virtual Club, for you. And we moving forward with the next talk. It's called Portal Design and Fabrication of Incidence-Driven Screens. And it's from a large group of authors, Said Wahab Hosseini, Usman Alim, Ali Matavi, Amiri, Laura Oelberg, and Joshua Tserum. So, Wahab, you can present.
Hello. So first of all, thank you for joining this conference and this specific presentation. I will be presenting design and fabrication of incidence-driven screens, or what we call portal. This work has been inspired by dozens of works in computer graphics, as well as arts and architecture. But most importantly, the mirror of Galadriel, a magic mirror that shows objects that do not exist in the immediate environment. What does that mean? Portal, generally speaking, is a structure composed of cellular mirrors that create an image by reflecting colors from another image that acts as a palette. Here, the Mona Lisa is our palette, and it's going to lend us some colors that's going to be used to produce other artworks. So in a few slides, I'm going to show you what that means. As I said, on the left, we have this palette, and then on the right, we have this grid of cells. So if we decompose our palette like this, and simply borrow that colored area and place it here on the right panel, and simply doing that for every single cell on the right grid. So for example, here we're gonna borrow the fingertips there. And like I said, we're gonna do that for every single cell. We're gonna have something that has got a meaning and it doesn't actually exist. What we're gonna do here is actually doing the same thing by means of reflection. And this is the result, but the low result. At the end of this presentation, I'm gonna present the high resolution results as well. First things, methodology. In a few words, again, the first step is image sampling. Here in image A is our palette, and it's gonna be divided into a number of blocks. Image B is produced by Portal. And each cell of image B corresponds to a mirror on Portal. Image C is sampled coarsely by cells, and the color of each mirror in Portal should be as close as possible to its corresponding cell on image C. Another step in our methodology is match finding algorithm. I have to stress that we are using Euclidean color difference metric, meaning that every RGB value here is being treated as coordinates in space. However, we can use other metrics, for example, perception-oriented metrics that are based on human sight sensitivity, meaning that they put weight on red, green, and blue differently. Grid type. Another point here in our methodology is to think about grid type. However, it is totally, our algorithm is totally independent toward grid type. But generally speaking, hex grids have lower quantization error in comparison with quadrilateral and triangular grids. But like I said, our methodology is not dependent on the form of the grid, and we can choose any of them. And it heavily depends on the aesthetic features within the image that we want to regenerate. For example, here, as you can see, this composition by Mondrian, hexagonal grid may fail to flawlessly represent straight lines as opposed to quad grid. And of course, resolution. Like I said, I'm going to present high resolution results as well. But we know that high resolution is plausible through higher number of blocks and consequently higher number of mirror cells. In this image, we have on image B, actually, we have these blocks of about 4,800 blocks and 540 blocks on image C. Another point is point of view, another factor to consider in my methodology. And I'm going to call that the privilege point. And it can be selected anywhere as long as both images are visible within humans' cone of vision, and there's no occlusion from one image to another. Another concern here, though, is the fabrication process, meaning that both images should remain within arm's reach to facilitate the process of fabrication. Optimization. So any degree, generally speaking, this is a viewpoint-driven perception. So any degree of deviation from the privilege point would cause imperfection of the result. What we did was that instead of dealing with one ray per block, we decided to deal with beam of rays per block so that slight deviation wouldn't cause imperfection. Image B here is generated with, again, 4,800 blocks, each of which is assigned average RGB value of its own pixels. Image C, on the other hand, is generated with average RGB value of a neighborhood, embracing that block and its adjacent blocks. That helps us tackle viewpoint perturbation. Fabrication. The only parts, the most important thing is to consider that mirrors are the only parts that need to be glued in their positions. And we use that notch stem mechanism to expedite the fabrication and work quite well. Also, we have some prototypes, both in quad and hex grids. And we also ran an experiment to find out the ideal notch inward offset for snug fit joinery out of a 5mm thick MDF sheet. And that was 0.021 millimeters. And in order to facilitate the fabrication, we also worked on labeling on front side of the stems and the right side of the notches so that we can match them easier. Results. Well, earlier I mentioned optimization. So here what you see is vertical deviation from the view, the privilege point, and horizontal deviation from the privilege point. The image on the red frame, for example, as you can see, -6 degrees on vertical deviation has got some issues as opposed to the image on blue frame, which is the result after optimization. And you can easily compare them to the one on green frame that's been rendered from the privilege point. And of course, we have our fabrication results and actually the fabrication and calibration process using this assisting dots on the palette. And of course, we have, again, a lower resolution result on the lower right corner. Okay, so let's take a look at the high resolution results here. Mirrors are getting oriented. And again, another result here. Another one. And we, of course, we decided to use different methods of paintings and arts in order to see how Portal reacts to different methods in terms of grids, in terms of color matching and everything. And that pretty much covers everything about the paper. Of course, there are more technical details in the paper and discussions, but that was my presentation. Thank you very much.
Thank you. Any questions?
Yeah, so I guess the source image is basically a filter that limits the collection of colors that you can possibly reproduce, because if there's no bright red, then you'll never see any bright red. So I would think that an artificial source image that would simply be stripes of the complete hue circle with, with different brightnesses, almost like the little panel that you get in Photoshop to pick a particular color. That would be like the best source, because then it would give you all possible colors that you might ever need. So to what degree have you thought about the limitations that a particular source image would then present to reproduce an image that you would like to reproduce as well as possible?
Thank you for bringing this up. Yes, as you mentioned, the palette has got limitations in terms of colors, and that limitation will be reflected directly on the results of Portal. But the idea was to make that like a magical result. We have Mona Lisa, and the reflection will be self-portrait of Van Gogh. But what you suggested totally works, and we're going to have better results in terms of color matching, I can say. But we're going to lose that magical aspect of Portal.
What is the highest resolution actual result that you have produced by actually mounting little mirrors of little posts? Have you gone to some experiment that produces some acceptable results, or is that just not really feasible?
So the highest resolution that we tried was the results that I showed here, 4,800 cells, 4,800 mirrors actually. We definitely could have gone higher, but as you know, it's gonna take more time to render, and it's gonna be way harder, I can say, to think about the fabrication. So our fabrication was in 540 cells only, but the highest number we went was 4,800, as I said.
So I'm still a little confused. So you actually put 4,000 mirrors on little stems and make a real physical representation of that, not just a simulation thereof, or what?
Yes, that's right. That's not a simulation. That's the actual result. That's
impressive. How how long did it actually take you to put the physical thing together and mount all these mirrors and everything like that? I mean, and how many people were involved doing this?
Well, the fabrication one, like I said, 540 mirrors, and I personally was involved in the fabrication process. And I've mentioned that in a paper that it took roughly around, as far as I remember, it was around 80 man-hours to laser cut everything and assemble everything, glue the mirrors, and take the results.
Wow, that is incredibly impressive. Yeah, that's superb. Wonderful. Congratulations.
Thank you very much, sir. Thank you very much.
By the way, I've got one more question. Following the question from Carla a few minutes ago. So, have you tried to use the different styles of paintings? So, like not using traditional, but maybe using some cubism, or well, map Picasso into, I don't know, some expressionists?
Thank you for asking this question. Like I said, that was one of our goals to evaluate the functionality of Portal under different styles of paintings. This one, for example, as you can see, this one is fairly close, relatively close to Cubism, and the grade that worked here very well was quad. On this totally different painting, you can see that we tried it as well, but this one we had to go for hex grids. Again, different style, different era, and as you can see, contemporary paintings and arts. And this one is, again, very much close to Cubism. And the results were quite acceptable in terms of the result, in terms of the resolution that we went after. So yeah, that's all.
Thank you. Actually, I think that's Mona Lisa Chumadonna would be like a good concept per se.
This one? Oh,
Yes. So something
sure.
like something like a subtle message of that. Anyway, thank you. Thank you
Exactly.
very much for your talk. It was a very great talk.
Thank you, sir.
And so we move forward with the last presentation for today. And that's a presentation from Carlos Sequin, and it's called Symmetrical Vortex Knots. So Carla, after you, please.
Okay, let me see. I can set this up here. Okay, I hope that works. I am essentially, let's see, shift that over a little bit here. Can I do that? Yes. So slides are in the middle. That leaves room if you want to see my talking head on the right, but I suggest you really look at the slides rather than the talking head. And as a little extra benefit, if somehow the sound is bad, then you see the stories I'd like to tell at the bottom. And I have put these slides also up on my homepage under Talks 2020. And so if later you want to see again what the story was, then you find there the slides, you know, with the text underneath. So here we go. For a long time, I've had an interest in turning mathematical knots into aesthetically pleasing sculptures. And for several semesters, I ran a project labeled The Beauty of Knots. The participating undergraduate students were asked to pick a simple knot from the knot table and to turn it into a nice 3D sculpture. Some rather unassuming knots turned out to have actually some extra hidden symmetries, and the students often exploited those symmetries. Here is the example of knot 5 sub 2. The twofold rotational symmetry axis is actually implied by the diagram that you find in the knot table. And in this 3D sculpture, that symmetry has been maintained, even though the shapes of the various lobes are now quite different. On the other hand, for knot 6 sub 1, the diagram in the table does not show any symmetry at all. But by playing around with some rope and with some pipe cleaners, one can quickly find that indeed this knot also can exhibit C2 symmetry, which has been actually done in this particular sculpture. So now my goal is to create visualization models and sculptural maquettes of more complicated mathematical knots, but with as much symmetry as possible. I would love to see a knot with, say, cube octahedral symmetry. And maybe you think the green thing here, that's it. But no, this green thing neither has octahedral symmetry, nor is it actually a knot. It is really a link of several separate strands. And it turns out that many high-order symmetries are not compatible with mathematical knots at all. So what are the possible symmetries? Well, knots are finite objects, and that means that they must fall into one of 14 possible symmetry families. First, there are the 7 symmetry groups that are derived from the Platonic solids, shown in the upper half. And then below that are 7 more families, and they are derived from the 7 Friese symmetries. All 14 symmetry families have been beautifully illustrated by David Swart, who actually took the trouble to find matching soccer balls for all of them. However, it turns out most of these symmetries are not applicable to knots at all, because knots have to be composed of one single non-self-intersecting loop. In 1985, Greenbaum and Shepard showed that knots cannot have more than one axis of rotational degree 3 or higher. I skipped the details of the proof, you can look at that later, but the upshot is none of the Platonic solids are applicable to true prime knots. They also showed that knots can only fall into 5 of the cylindrical families, but if we exclude the trivial knot, a simple torus, and if we exclude compound knots and focus on truly prime knots, then there are only 3 of these families left that knots can possibly assume. First, there's the cyclic group Cn, and then the dihedral one, Dn, and finally the glide symmetry with S2n. Here is a simple argument that shows that prime knot cannot possess mirror symmetry. First, assume that there is a knot with a single mirror plane, and that means that there must be 2 separate blocks of that knot that are mirror images of one another. But in order to form this into a knot, we of course need to connect them. And we can do this with the 2 yellow arches shown on the left. However, shown like that, it's clear this is a compound knot. It is not a prime knot, because then we would have to have more links across the mirror plane. So if we try to add 2 more links across the mirror plane, shown in orange, but we maintain the overall symmetry, then bad luck, this is no longer a knot. Because of that symmetry condition, it is now a link of 2 separate knots. So knots cannot have plane mirror image if they're true prime knots. So in the end, we then end up that there are only 3 possible symmetries that knots can assume. You know, the simple cyclic rotation around the single axis with a valence of degree n, or the same thing but with a dihedral symmetry, which adds extra C2 flip axes in the equatorial plane, which are marked here in the middle diagram by the blue dots. And finally, glide symmetry with a glide plane in the equator. And then you're essentially turning and flipping and turning and flipping to produce the kind of symmetry that you get when you take the strip at the bottom and wrap it around the cylinder. Well, these kind of symmetries are really the hallmarks of torus knots. In a torus knot, kind of S and T, the first number in parentheses gives the symmetry or the valence, you know, I sometimes call it N, of the rotational axis. And then the second number, T, tells how many turns the filament actually takes around the hole. So now I've turned the game around. Rather than finding out what is the possible highest symmetry of any given knots that I may have to start from, I just start to construct something that has high symmetries. And maybe only later, I will then try to find out where in the knot table a particular knot might appear. But in some way, torus knots are really dull. As you can see in the bottom row, when N or T go to really high numbers, these things don't look like nice Gordian knots. They look more like radiator tubes, you know, in a cooling system. But we can use the torus knot as a starting point and turn them into something more interesting. Here I started with the torus knot 3,5, shown on the left, and I kind of flattened it, and eventually I squash it completely flat. And of course, now it has intersection, but I get this nice template on the right, which has 3 times 5 minus 1 crossings. And on this template now, I can choose at every crossing point which one of the 2 strands should go on top and which one at the bottom. Of course, when doing this, I want to maintain the 3-fold rotational symmetry. I call all the knots that are emerging from this particular approach vortex knots, because in all cases, the filament will continue to run around the central hole in a purely monotonic way, in the same way that in a spiraling vortex, you know, the water turns around monotonically around the central axis. This is a quick way to generate additional highly symmetrical knots from a simple torus knots. As a first option, I may simply make the knot truly alternating. While the original torus knot corresponds to knot 10 sub 124 in the table, the modified alternating knot is now the knot 12A sub 1019. So for every torus knot, we can obtain a corresponding alternating braid. And these braids are known as Turk's head knots. But of course, we can also change the crossing pattern in more radical and more, less regular ways. It turns out that these are all the options for the family of 3,5 vortex knots. At the top left is the original torus knot with a crossing pattern O, 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 U, 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 U. And that means that every strand has to run over the other 4 strands first, and then has to run underneath the other 4 strands before it comes back to where it starts. Below this one on the lower left, you find the alternating Turk's head knots with simple OU, OU, OU pattern and so on. And then there are 4 other patterns. For instance, on the top right, there is the double over, double under crossing pattern. Now, all the shown crossing patterns must be repeated 3 times to make up the full knot. So this is the characterization of how we construct vortex knots. First, I draw the S, T circular braid template. Then I specify how to arrange the over and under crossings. An initial torus knot with just 3 turns has only 2 possible symmetrical crossing pattern options. Either it's the torus knot or it's the alternating knot. But for a circular braid with 4 turns, we can get more crossing patterns. For instance, now we also have the pattern OOU, OUU. And as we go to ever more turns, the number of possible crossing patterns actually increases exponentially. Now, cowboys, they love the Turk's head knots, but of course, they don't use them as flat circular braids. They typically wind them around a cylindrical object, such as the handle of a switch, or they wrap it around a more spherical shape, as you can see here. Here are 2 close-ups made from rawhide, which are just strips from the hide of a cow, or from latigo leather, which is colored strips that are tarnished and hide, and then infused with some materials, and they are often also immersed with waxes, so they get nice and shiny, as you can see on the right-hand side. So we can do the same thing with all of our vortex knots. Here I have shrink-wrapped the braid around the sphere with a diameter that's only slightly larger than the width of the braid. And this means that now the braid covers most of the domain of the sphere. I call the results ball knots. All examples shown here are strictly alternating braids. The first parameter indicates the order of the vertical rotational symmetry axis. And the second parameter tells how many times the filament travels around that particular axis. It turns out that if the turn number is even, then we obtain a knot with dihedral symmetry, ds. But if it is odd, then the knot will have glide symmetry, s to s. And here are 3 more examples of alternating ball knots S, T. But now let's look at a different crossing pattern. This knot has the double over, double under crossing pattern OOUU, OOUU. I show 4 different geometrical realizations of it. First, as a circular braid on the left, then as a cylindrical braid, then as a ball knot, and then finally mapped into a tetrahedral frame where the top and the bottom edges exhibit a double covering of the 2 linked loops. The last 2 models exhibit S4 symmetry. Now, all these are still the same simple mathematical knot 6 sub 2. Now, I'm using the same crossing pattern OOUU, OOUU in knots with a higher rotational symmetry. All these knots have 5 turns and they all exhibit glide symmetry. In the middle range, in the middle image there, I have split the parts into upper and lower lobes to make the glide symmetry as easy to see as possible. But it's still pretty hard to see in a static image. So you really want to have a 3D model in your hand so you can play with it. Now I want to broaden the concept of vortex knots. In all the vortex knots derived from torus knots in the way I showed before, the knot strand undulates in a regular manner as shown on the white line in the middle. But now I want to be more general and allow this knot strand to undulate with smaller amplitudes as shown by the red line, but it still must be going monotonically from left to right. In order to obtain some symmetry in our knots, we need to repeat the given braid pattern more than once. On the left, I start with the braid representation of knot 6 sub 3. And beside it, I show a possible configuration of this particular knot shown as a simple cylindrical braid. In that form, it doesn't really have any symmetry. But if we repeat that braid pattern once and close it into a cylindrical loop, we now obtain a knot with twofold rotational symmetry, as shown in the middle. And then on the right, I show that same knot again as a ball knot, but it's exactly the same topology. And here is another example that starts with the minimum braid representation of knot 10 sub 43. Here I wrapped three concatenated copies of the braid around a cylinder to form another vortex knot, now with threefold rotational symmetry. This shows the general approach. I start with an arbitrary piece of a braid and then place S replicas around a central rotation axis, which gives you symmetry CS. But in doing so, I have to make sure that the result is still a simple knot. As a bad counterexample, on the right there, the red strand will form a simple loop all by itself, and the yellow ones, they will add up to a particular complicated knot. But of course, altogether, it's not a single knot, it's just a link. And then we have to be even more careful, because for some given braid, there may be a number of iterations that work just fine, but a different number of replicas may result in a link. So what's the limit of forming these kind of symmetrical vortex knots? To obtain a true vortex knot, we need to pick a proper braid, one that progresses unidirectionally. This then leads to a strand that monotonely circulates around the center. The thing in the lower left is not a proper braid because one of the strands loops back on itself. And the thing on the right is not a vortex knot because, again, it does not monotonically go around the central point. Here is another example of a very intriguing symmetrical loop, but it's not a monotone loop, and it leads to an interesting 3D knot shown on the right, but it is not a vortex knot. To wrap this up, let's go back to two very simple knots. The torus knot 2, 3 happens to be the well-known trefoil knot. If we turn this one into an alternating knot, then it becomes the figure 8 knot. On the right, the torus knot 3, 4 corresponds to knot 8 sub 19 in the table. And once this has been made alternating, it becomes the Chinese button knot, which is knot 9 sub 40. Even these two very simple examples, however, can lead to very attractive sculptures. And here are two sculptures corresponding to these alternating knots. I have embellished them in several ways. On the left, I have wrapped the braid pattern around a conical shape rather than a cylindrical shape to obtain the flared out lobes at the top. In both cases, I have also used a crescent-like cross-section rather than a boring circle sweep. This makes it clear that what one does with the geometry of a knot is even more important than what one does with the topology if you want to make a nice sculpture. The master geometry for these knots has been done in ABS on a fused deposition modeling 3D printer. And this was then used as a classical investment casting process where Steve Reinmuth simply had to heat up the oven somewhat more. So the ABS or the PLA, they sublimate very nicely, leaving no residue. And so you can then essentially recreate your original in bronze. And Steve Reinmuth in his bronze studio in Eugene, Oregon, has done a really nice job. He's also the one that applied these beautiful patinas. Okay, thank you for your attention. I'm glad to take questions.
Thank you, Carla. Any questions from the audience? Yes, we got one question in the chat. Can you see the chat? So the first question is any pattern of crossing chosen for vortex nodes guaranteed not to give rise to the unknown?
Sorry, I didn't quite get that question. Can you run that by me again?
Sorry, Matt Bright here. I can do, so for any pattern of, so having selected a pattern of over and under crossings from your flattened torus knot,
Yes.
Is any pattern you choose guaranteed not to be effectively the trivial knot?
Think about that. Well, of course, if you start with the torus knot 1-1, the trigger knot, right? And if you add in a template, you still have just a ring, and there's absolutely nothing you can do with changing any crossings because there are none. But I believe if you have a true torus knot, then first of all, you can always make it alternating, and that's always a knot that is at least, but practically all the time, more complicated than the original torus knot. It's a true knot, and it's not going to be a link as long as S and T are mutually prime. If you start with a torus knot that has not mutually prime number, it's not really a knot, it's already starting out as a link. And of course, you cannot really fix that by just changing the over and under processes.
Sure. If I might ask a follow-up question quickly, which I had written in the chat, have you found any relationship between the topological invariance of knots, so there are lots of known topological invariants, and the symmetries that it exhibits, or that it can exhibit?
No, I have not. No, I'm not a mathematician. I'm not really a specialist. So I'm not saying it doesn't exist. I have, kind of dabbled a little bit in that, but not conclusively. At the Bridges conference together with one of my students, we'll have a paper that shows how you might tease out symmetries from a given knot. If a complicated knot, maybe 15 crossings or so, you don't even know what knot it is in the knot table. And the question is, how can we see that this knot finds a geometrical representation that has more symmetry? Now clearly, playing these pipe dreams, and that's probably actually the most efficient way. If you try it in computer graphics in the plane, and you use randomized moves where you carefully move lobes around so that the knot topology doesn't change, it's very, very tedious, and you really don't know what moves to make in order to enhance the symmetry of that knot. But then they found out that if you start with a chord diagram of the knot, you can do the equivalent of randomized moves in that diagram as well. But it's now a little easier to see because it's a very formal representation of the knot. Which move might actually lead to a more symmetrical configuration. Again, we do not have an algorithm that clearly says what moves you should take next, but it makes experimentation a little bit easier. And then we have been able to distill out some symmetries from knots that were clearly not implied in the first place, and that we could not have found by any other way. But this whole issue about what's the maximal symmetry or not, I think is still wide open, and I haven't found anybody who can help me along in this direction.
Thank you.
Thank you. Well, I think that we don't have any further questions. So I guess that wraps up the session quite nicely. We had 4 very interesting and very different works. And I hope all who joined the session today found it quite useful and interesting. And I guess that more or less wraps up the first day of SMI, because the next session, which will take place today in the timetable, is, well, for me it will be tomorrow night's French time. So thank you for presenters, thank you for the audience, and just to remind you that FASE poster sessions will take place tomorrow, 6 o'clock French time, and well, whatever time it will be for you. So please join us for FASE posters, and hopefully you'll see 4 more works which will be quite interesting and unusual. That's for sure. So thank you very much for coming, and yeah, see you tomorrow indeed.
Thanks.